In this video, we will study the first law of thermodynamics, one of the great laws that tells us how to solve problems. We already had the 0th law of thermodynamics, which basically gave us a definition of temperature. The first law of thermodynamics basically tells you that energy is conserved. It is the conservation of energy statement for dealing with even the microscopic world. The change in the internal energy of a system, it says, is equal to the heat transferred to the system minus the work done by the system. The change in the energy inside the system, the internal energy, is equal to any energy you transfer to the system by heat minus any energy you take out from the system as work. Now, if you do negative work, if you take a negative 10 joules of energy by work, then that becomes a minus of a minus, means that a negative work means you put energy in the system. Likewise, if your system gives off energy as heat, then that's negative Q, and that reduces the internal energy of the system. Now, I keep using the word system. The system is whatever you define that you want to calculate the energy to be. It could be a human being, it might be a piston, it could be a laser, it could be the sun. In this case, let's say that it's this gas in here. So when I talk about the internal energy, I'm talking about the internal energy of this gas that I've got in red. The piston represents an interface between the gas on one side, the system, and everything else in the universe. The rest of the universe is called the environment. Doesn't have to be a tree or anything. For instance, you could be the environment if the system I was talking about might be the car seat, and you're sitting on the car seat. If you're outside the system, you're part of the environment. What we're saying in this thing is that if the gas does work on the piston, which is part of the environment, then that is taking energy. And I'm going to draw that work with a W with an arrow saying that positive W means it leaves the system. On the other hand, for heat, I'm going to draw Q going into the system. That's because I'm going to heat it with some sort of little fire. So you have to represent, remember, heat and work are transfers, flows of energy. They therefore have to have arrows indicating what you define as a positive flow. The sign convention up here is dictated by the choice of the arrows. It didn't have to be this way. There are some textbooks that choose to make W point in as well, in which case they make this a plus. There are some that make W go in and Q go out, which puts a minus Q and a plus W. The arrows have to match up with the equation. I'm saying I'm going to add a positive Q, say plus 3 joules. If it goes into the system, that should raise delta U by 3 joules. I'm going to say if you do a positive work of 5 joules, that's 5 joules that left the system. That was an expenditure of money. So your bank account goes down. So if you want to find out how much the bank account goes up, and you spent $5, it went up a negative 5. It went down, not up. This is simply, like I said, the statement of the law of the conservation of energy. Now, this equation is very powerful. I have a formula I've already shown you for calculating how to calculate work. We've talked previously about formulas, for instance, to calculate Q. If I know both of these over some process, I can calculate the change in U. But we also said that U was connected for systems like gases to T. So if I can compute the Q, the W, I can find a change in U. I can find the change in the temperature of the system. I likewise could use a change in the temperature of the system to find the change in U. If I knew how much W I had, I could calculate the heat that was either absorbed or released. It's simply a matter of you tell me some things and I work with 1, 2, or 3 of these, depending on which one. There are 3 things. If you give me 2 of them, I can get the third. Now, there's a lot of different ways you can set the problem up. And in fact, there's a lot of different situations that are useful. These processes in which you change whether you're doing work or putting heat or changing the temperature are called thermodynamic processes. One of the most famous is called an isobaric process. An isobaric process is a process in which you do everything under constant pressure. So let me draw a PV diagram. There's P, there's V, and you were at state A. And you had some volume VA. And you stayed at constant pressure, and you moved to some new state, B, with some new volume, VB. Well, in that case, I can determine very easily the work done. It's the area under the curve, and in this case, that curve is easy. The work equals the area of the rectangle. So W will equal the height, which is P, times VB minus VA. So it's P delta V. So if you tell me the pressure and you tell me the change in the volume, I can immediately calculate the work. Let me put that right here. Now, that doesn't tell me Q, and it doesn't tell me delta U. So if you have to tell me T, I could tell you what delta U is. Or if you told me what Q is, and I know W, then I can use that to calculate delta U. The only thing I know for sure in an isobaric process from this graph is I can easily calculate work. That's what I can do. And I was assuming that I was going from A to B. Another process, isovolumetric. Iso meaning constant, volumetric meaning volume. So a process performed under constant volume. I'll draw again a PV diagram. And in this case, the process goes from some pressure, say pressure PA, and it goes without changing volume to say some new pressure PB. There is no area under the curve. There was no displacement, if you would, of a piston if it was under this thing. You might keep the piston locked in place. Put in a pin in the side of the container so the piston can't move. And what you did was you went in here and put an ice cube on this thing. And that cooled the gas, so the gas molecules weren't banging as hard, so they don't exert as great a pressure. So the pressure went down, but the volume was unchanged because you pinned this piston. That would be an example of an isovolumetric process. The work is 0 joules. Consequently, delta U has got to be equal to Q. So if I take heat out by putting an ice cube, then I will lower the internal energy of the system, and I will consequently lower its temperature. Isothermal processes. An isothermal process is a process in which the temperature doesn't change. But since the temperature is related to the internal energy, if the temperature is constant, the internal energy of the system is constant. So in this case, delta U is equal to 0. And we get Q has to equal W. So in an isothermal process, any energy that is absorbed as heat is then not kept in the bank account, but is used to do work. So an example of that could be that you have a system like this with some piston, and you heat, and that piston moves up, keeping the temperature of the gas a constant. Adiabatic processes. Another important process is an adiabatic process. An adiabatic process is a process in which no thermal energy is transferred by heat. So for an adiabatic, Q is 0. So therefore, the change in the internal energy is minus the work. If the gas does work, then the internal energy of the system is decreased. If the gas does negative work, then the internal energy of the system is increased. An example of that would be to have a very good insulating insulator and have a piston and have, for instance, some sort of pin. So you have this at very high pressure. And then you pull that pin, and this piston goes up. When that happens, the internal energy of the gas in here has to go down. And in fact, that energy goes to give kinetic energy to the piston. That thermal expansion will cause this gas to cool, and this is one of the ways to cool gases. And in fact, if you take CO2 and do this very fast, you convert it to a solid form called dry ice. Now on the other hand, you could do work against the piston, which is negative work to the gas, by pushing down on this piston, compressing the gas. And when you do that, the gas internal energy goes up and you get a heated gas. This is done in combustion engines, for instance. The last one, cyclic processes. Cyclic processes are processes that return to their initial state. So they start some here and they go down to some place, and then they come back to where they started. Consequently, since they end up where they start, delta U is 0. This area inside this curve, assuming we went this way, is the work. If we go this direction, it would be positive work. If we went the other way, it'd be negative work, because it would have a negative area. Alright, that covers this video.